Hello everyone, and welcome. I'm excited to introduce you to our presentation today. We'll be exploring a step-by-step guide to learn R. This session is designed to help you get started with R programming, covering the essentials and guiding you through the learning process. We'll go over the basics, some useful tips, and practical steps to become confident in using R. Let's dive in and get started on this exciting journey. Welcome to the Data Analysis course. I'm Venkat Reddy, and today we'll be exploring the key steps to mastering data analysis with R. We'll start with step 1, which is understanding the basics of R. This foundational knowledge is crucial because it sets the stage for everything else we'll do. Getting comfortable with R's syntax and environment makes all subsequent steps much smoother. Next, we move on to step 2, data manipulations. This is where we learn how to clean, transform, and organize data efficiently. These skills are vital because good analysis depends on well-prepared data. Finally, step 3 covers functions, graphs, and analytics. Here, we'll dive into creating reusable code with functions, visualizing data through graphs, and performing advanced analytics to uncover meaningful insights. Throughout this course, these topics will build upon each other, giving you a comprehensive toolkit for data analysis. So, let's get started with the basics of R and see how these steps translate into practical skills for your data projects. Let's start with the basics of R first. R is a powerful programming language specifically designed for statistical computing and data analysis. It's widely used by data scientists and analysts because of its flexibility and extensive library of packages. When we talk about the basics, we're referring to understanding how R handles data, how to write simple commands, and how to navigate its environment. Grasping these fundamentals is crucial because they form the foundation for everything else we'll explore later in this course. Think of it as learning the alphabet before you start reading and writing in a language. Once you're comfortable with these basics, you'll find that R becomes a very intuitive tool for transforming raw data into meaningful insights. So, as we move forward, keep in mind that mastering these initial concepts will make the more advanced topics much easier to understand. Welcome to this section on the basics of R. Here, we'll cover a range of fundamental topics that are essential for anyone starting with R first. We'll look at what R actually is. It's a powerful programming language specifically designed for data analysis and statistical computing. Then, we'll explore RStudio, which is the most popular interface to work with R, making coding and analysis much more manageable. Next, we'll discuss the R environment. Think of it as your workspace where all your data, variables, and functions live during your session. Understanding this environment helps you keep track of your work efficiently. We'll then move on to the basic operations in R, which include creating variables, performing calculations, and manipulating data. Following that, we'll talk about R packages. These are collections of functions and data that extend R's capabilities, allowing you to do more complex analyses with ease. We'll also cover vectors and data frames, which are the core data structures in R. Vectors are simple, one-dimensional collections of data, while data frames are like tables, allowing you to organize and analyze data in a structured way. Then, we'll see how to write R scripts and save your work, which is crucial for reproducibility and future reference. I'll also guide you through writing your very first R program, so you get hands-on experience right away. We'll look at functions in R, which are blocks of code designed to perform specific tasks efficiently. Additionally, I'll show you how to access R help files, which are invaluable resources when you're learning or troubleshooting. Finally, we'll briefly discuss the step-by-step process to grasp the basics of R, setting a solid foundation for everything else you'll learn in this course. All these points are interconnected and will help you develop confidence in using R for your data analysis projects. Let's talk about the programming environment, which is a crucial part of the data analysis course. This environment runs smoothly on a variety of platforms, including Windows, Unix, and macOS, making it versatile and accessible for many users. It offers an unparalleled platform for programming new statistical methods, allowing us to implement innovative ideas in a straightforward and user-friendly way. One of the key features is that it is object-oriented, which helps in organizing complex data and functions efficiently. It's also open source, meaning we can freely access and modify the software, fostering collaboration and continuous improvement. Additionally, it boasts excellent graphics capabilities, making data visualization clear and impactful. Lastly, it's supported by a large user network, so there's a vibrant community for support, sharing knowledge, and troubleshooting. Overall, this environment is a powerful tool that enhances our ability to perform sophisticated data analysis seamlessly across different systems. Welcome to slide 6 of our data analysis course. I'm Venkat Reddy, and today we'll be focusing on how to get started with R. If you're wondering how to find R, just Google it or visit the CRAN, which stands for the Comprehensive R Archive Network. The official website is http://www.rproject.org. From there, you can easily download R for your computer. This step is essential because R is the main tool we'll be using throughout this course for data analysis. So, make sure to download and install it before we move forward. Remember, having R ready is the first step towards becoming proficient in data analysis. Welcome to slide 7 of 106 in our data analysis course. I'm Venkat Reddy, and today we'll focus on the essentials of data analysis. As we progress through this course, you'll see how data analysis is a critical skill that unlocks insights and drives informed decision-making. This slide introduces the course title and my name, setting the stage for the knowledge you'll gain. Remember, the key to mastering data analysis is understanding the core concepts and applying them practically. So, let's keep this in mind as we move forward and explore the fascinating world of data together. Welcome to slide 8 of 106. Here, we focus on the data analysis course, which is led by Venkat Reddy. This course provides a comprehensive introduction to data analysis techniques and tools. One of the key tools we'll be using throughout the course is RStudio. RStudio is a powerful, user-friendly environment for working with R, which is one of the most popular programming languages for data analysis. It helps us organize our work, write code efficiently, and visualize data effectively. As we progress, you'll see how RStudio becomes an essential part of turning raw data into meaningful insights. This slide highlights the importance of mastering these tools to succeed in the overall data analysis journey. Welcome to slide 9 of our data analysis course. I'm Venkat Reddy, and today we'll be focusing on the console. The console is an essential tool for data analysis because it allows us to interact directly with our data and run commands in real time. Think of it as our command center where we can input code, see immediate results, and make quick adjustments. This real-time interaction is crucial for exploring datasets, testing hypotheses, and debugging. As we progress through the course, mastering the console will help you become more efficient and confident in handling data. So, let's dive in and explore the powerful features of the console together. Welcome to slide 10 of our data analysis course. Here, we're focusing on some fundamental R commands and functions that you'll use frequently. First, you'll see simple calculations like 2 plus 2, which is a straightforward example of basic arithmetic in R. Then, we move on to logarithmic functions, like log of 10, which is important for data transformation and normalization. The exp function, like exp of 5, is the inverse of the log and useful in exponential growth models. You'll also notice the help command, help, log, which is essential for learning about any function directly within R. Think of it as your quick reference guide. The demo on graphics is about creating visual representations of data, because, as you'll see later, pretty pictures really help in understanding and communicating insights. Next, we have the summary function applied to the air quality dataset, which provides a quick overview of key statistics: mean, median, min, max, making it easier to grasp the data's distribution at a glance. Finally, there's a mention of RDemo, indicating practical demonstrations that bring all these concepts together. Throughout this course, these tools will help you analyze data more effectively, so mastering them early on will set a solid foundation for your data analysis journey. In an R session, all the objects you create are stored in something called temporary or working memory. Think of it as a scratch pad where R keeps track of all your data and variables while you're working on your analysis. When you enter commands, You do so interactively at the R user prompt, which is like having a conversation with R. You can also use the up and down arrow keys to scroll through your command history, making it easy to revisit or modify previous commands. To see what objects you currently have in your workspace, you can use the list objects command, which is simply ls. If you want to remove some objects to keep your workspace clean, you can use rem. And if you want to look at your data, the data function helps you load or access built-in datasets. Understanding how R manages objects in your workspace is crucial because it helps you keep track of your data and avoid clutter, especially as your analysis grows more complex. Remember, everything is stored temporarily during your session, so saving important objects outside R is essential if you want to keep them long-term. Welcome to slide 12 of our data analysis course. Today, I want to focus on the importance of naming conventions in R. As you know, variable names in R must start with a letter, either uppercase or lowercase. After that, they can include letters, digits, and even periods. It's essential to remember that R is a case-sensitive language. This means that my data and my data are considered two completely different variables. Paying attention to this detail helps prevent bugs and confusion in your code. When naming your variables, stick to clear and consistent conventions. This not only makes your code more readable, but also easier to maintain. Overall, understanding and following proper naming conventions is a fundamental part of writing clean, effective R scripts. Let's take a closer look at some basic data assignment in R. When assigning data to an object, we can use symbols like or equals. For example, if I write x7, that means I'm assigning the value 7 to the object x. Similarly, we can create vectors in several ways. Using xc 1, 2, 3, 4, 5, 6, 7 creates a vector with those specific numbers. Alternatively, we can write 1, 7, which generates a sequence from 1 to 7. And even more simply, x1, 4 creates a sequence from 1 to 4. It's important to note that assigning data to objects can be done in different ways, but the key point is that and equals are all valid assignment operators. Also, if you see equals equals, that's a comparison operator used to check if two things are equal. Keep in mind, there are many other notations and functions available in the base package of R, which you can explore further in the documentation. Understanding these basics of assignment is fundamental as we move forward in mastering R for data analysis. Welcome to slide 14 of our data analysis course. Today, we'll walk through some fundamental R commands and concepts that are essential for data analysis. First, we use the command xrnorm 10, mean equals 20, sd equals 5, to generate a sample of 10 random data points from a normal distribution with a mean of 20 and a standard deviation of 5. This helps us simulate data for practice. Then, simply typing x will display the generated data. Next, we calculate the mean of this data with mean x, which is crucial for understanding the central tendency. To store this value for later use, we assign it to a variable m using m_mean x. Typing m will show us that value. We then take the logarithm of the mean with log m, which can be useful in various transformations. Moving on, we subtract the mean from each data point with xm, highlighting how data points deviate from the average. Squaring these deviations with x, m2, emphasizes larger deviations, which are important in variance calculations. Summing these squared deviations using sum xm2 gives us the total squared deviation, a key step in understanding data spread. We also see commands like data to load built-in datasets and ls to list all objects in our current environment, keeping our workspace organized. Lastly, the slide mentions lab, working with R, which is where you'll practice these commands hands-on. All these steps are fundamental in analyzing data, helping us understand distributions, variability, and how to manipulate data efficiently in R. All right, let's talk about R and its structure. R consists of a core, which provides the basic functionalities, and then there are packages. These packages are like add-ons that contain additional functions that aren't available in the core R system. Think of them as tools that expand what you can do with R. Packages are essentially collections of R functions, data, and compiled code that work together to make your analysis more powerful. They follow a well-defined format, which makes installation straightforward, ensures proper documentation, and improves portability and reliability. When you first download R, you'll find that around 30 packages are installed automatically. Now, to see which packages are currently attached to your R session, you can use the search function. When you run search, it displays a list of attached packages, which we also call the search path. This helps you understand what tools are readily available for your current work. In summary, understanding how R packages work and how to check which ones are loaded is fundamental to effectively using R for data analysis. Now, let's talk about how to work with packages in R, which is a key part of data analysis. First, you'll want to go to the Packages menu and select Install Package. When you do this, a list of available packages on your system will appear. You can choose one of these packages that you need for your analysis. After selecting it, just click OK, and the package will be attached to your current R session. This is essential because it makes the functions and data within that package accessible to you. Additionally, you can use the library function to manage your packages. Not only does this attach a package, but it can also be used to list all the available libraries on your system, along with a short description of each. If you run the library function without any arguments, R will display all the libraries you have installed. This is a quick way to see what tools are at your disposal for your data analysis projects. Understanding how to install and load packages is fundamental because it expands R's capabilities, allowing you to perform more complex and efficient analyses. It's a core skill that ties into the overall theme of empowering your data analysis journey with the right tools. Welcome to slide 17 of our data analysis course. Today, we'll focus on downloading and installing the necessary packages. This step is crucial because these packages are the tools that will enable us to perform data analysis effectively. I'll walk you through how to find the right packages, download them safely, and install them properly on your system. Remember, having the right tools set up correctly lays a strong foundation for everything we'll cover later in the course. So, let's get started with ensuring your environment is ready for data analysis. Now, let's move on to the next step in our data analysis journey. Here, we're focusing on loading a package. In data analysis, packages are essential because they contain pre-built functions and tools that make our work much easier. Think of them as specialized toolkits that help us perform complex tasks efficiently. When we load a package, we're essentially bringing in these tools into our environment so we can start using them immediately. This step is crucial because it sets the foundation for the analysis we want to perform later. Remember, understanding how to load and utilize packages is key to streamlining your workflow and making your data analysis more powerful and effective. Now, let's talk about how to load data into R. There are several packages designed for this purpose. For example, RODBC, RMySQL, RPostgreSQL, and RSQLite are great for connecting R to various databases. If you're working with Microsoft Excel files, Excel Connect and XLSX allow you to read and write Excel documents seamlessly. The foreign package is particularly useful when you need to import data from other statistical software like SAS or SPSS. Moving on to data visualization, ggplot2 is one of the most powerful tools out there. It uses the grammar of graphics, which means you can create layered and highly customizable plots, perfect for detailed data analysis. For interactive, web-based graphics, ggvis is a fantastic choice, allowing you to build dynamic visualizations. If you're interested in 3D visualizations, RGL provides interactive 3D plots that can really help illustrate complex data structures. Lastly, HTML Widgets offers a quick way to develop interactive visualizations using JavaScript, making your data presentations more engaging and accessible online. All these packages are essential tools in the R ecosystem, enabling us to load, manipulate, and visualize data effectively, which ties back to our overall goal of mastering data analysis with R. Now, let's take a look at some of the key R packages used in predictive modeling. First up, we have the CAR package, which includes the ANOVA function. It's quite popular for creating type II and type III ANOVA tables, helping us understand the significance of predictors in our models. Moving on, the MGCV package specializes in generalized additive models, or GAMs, which are great for capturing nonlinear relationships in data. Next, the LME4 and NLME packages are essential for fitting linear and nonlinear mixed effects models. These are powerful when dealing with hierarchical or group data. The random forest package brings in machine learning techniques, specifically random forest methods, that excel in classification and regression tasks by combining multiple decision trees for better accuracy. The multcomp package provides tools for multiple comparison testing, which is crucial when we want to compare several groups simultaneously and control for false positives. For categorical data visualization and testing, VCD is very useful. Think of it as a toolkit for categorical variable analysis. Then there's GLNet, which offers lasso and elastic-net regression methods. These are especially helpful for dealing with high-dimensional data and include cross-validation to tune model parameters effectively. The survival package is tailored for survival analysis, allowing us to analyze time-to-event data, which is common in medical studies and reliability testing. Finally, the Carrot package acts as a comprehensive toolkit for training and evaluating both regression and classification models, streamlining the entire modeling process. Altogether, these packages form a versatile toolkit for advanced data analysis and predictive modeling, tying into the overall theme of leveraging R for robust statistical insights. All right, let's walk through the key steps for setting up our data analysis environment. First, we need to download the datasets package, which provides the raw data we'll be working with. Next, we'll download and attach the forecast package, essential for making predictions and analysis related to time series data. After that, we'll do the same for the cluster package, which helps in grouping similar data points together. Additionally, we'll install the plr package, which is particularly useful for string operations and data manipulation tasks. These steps are fundamental because they ensure our workspace is ready with all the necessary tools to perform comprehensive data analysis. Remember, having these packages properly installed and attached makes our workflows smoother and more efficient as we move forward in the course. Welcome to slide 22 of our data analysis course. Here, we're diving into some fundamental R data types that you'll encounter frequently. Let's start with vectors, which are the basic building blocks in R. Think of vectors as a simple collection of elements of the same type, like numbers or characters. They form the foundation for more complex data structures. Next, we have data frames, which are essentially collections of vectors organized into rows and columns, like a spreadsheet or a table. Data frames are crucial because they allow us to handle datasets with multiple variables. Moving on, lists are more flexible collections. They can hold different types of R objects, such as vectors, data frames, or even functions, making them very versatile. Other important types include matrices, which are two-dimensional arrays of elements all of the same type, factors, used for categorical data, and arrays, which are multi-dimensional generalizations of matrices. Understanding these data types is key because they form the foundation of data manipulation and analysis in R. Each type serves a specific purpose, and knowing when to use them helps us work more efficiently and effectively in our data analysis projects. Let's talk about the basic data structure in R, which is the vector. Vectors are actually the simplest objects in R. Think of them as an ordered list of primitive R objects, which can be numbers, strings, or logical values. They're fundamental because they serve as the building blocks for more complex data types in R. An important point to remember is that vectors are indexed starting at 1, not 0 like in some other programming languages. Creating a vector is straightforward using the C function, which concatenates elements into a single vector. For example, if you want to create a vector of names or numbers, you just list the elements inside C. Let me give you an example. If I assign name Venkat, I can check if this is a vector by using is vector name. Similarly, I can create a numeric variable like age 29 and verify its type with is vector age. Understanding vectors is crucial because they form the foundation of data manipulation in R. And mastering this concept will make working with data much easier and more efficient. Now let's look at some examples of R vectors. You can see here that we have variables like Smith and Rick representing names, and then we assign their ages and marks using the C function. The C stands for concatenate, which means we're combining multiple values into a single vector. For instance, age is a vector holding the ages 15, 17, 16, 15, and 16. Similarly, marks 1 and marks 2 are vectors containing different scores. It's important to understand that in R, vectors are a fundamental data structure, especially for handling data like this. When we say class, age, or class, marks, we're checking the type of these variables, and here, both are vectors. Recognizing that these variables are vectors helps us understand how R handles data efficiently and prepares for more complex analysis. So, in essence, vectors are the building blocks for data in R, and knowing how to create and manipulate them is crucial for any data analysis task. This foundation will support everything we do moving forward in this course. Let's take a look at some key features of working with vectors in data analysis. Most mathematical functions and operators can be directly applied to vectors without the need for loops, which makes the process much more efficient. For example, if we have an age vector, we can simply add 2 to each element by writing age plus 2. Similarly, if we want to increase all marks in a vector, we can do marks 1 minus or plus a number, like adding 10 to each element. We can also perform logical operations, such as checking if marks 1 is less than 80, or combining operations like adding marks 1 and marks 2 to get a total score. Then, dividing that total by some value, like the total number of subjects, gives us an average or other meaningful metric. Another important concept is creating sequences. For example, using the sec function, we can generate a sequence from 0 to 40 in steps of 4, which we might call formult. All of these examples highlight how R makes vector operations straightforward and powerful, allowing us to manipulate data efficiently and focus more on analysis rather than coding intricacies. This is a core part of working with data in R, especially in data analysis courses like this one. Now, let's talk about selecting elements in a vector, which is a fundamental part of data analysis in R. To access specific elements, we use the square brackets, or the operator. For example, if we want to select certain elements, we can specify their positions using either a single index or a vector of indexes. This way, we can precisely target the data points we're interested in. On the other hand, if we want to exclude certain elements, we can negate the indexes or the vector of indexes. This is done by putting a minus sign before the index or vector, which tells R to give us all elements except those specified. For example, if we have a vector called age 2, 5 will give us elements from position 2 to 5. If we want to exclude the second and third elements, we can write age minus 2, minus 4. Similarly, age minus 2 will give us all elements except the second one, and age minus 2, minus 4 excludes a range of elements. We can also modify specific elements directly. For instance, age 3 accesses the third element, and age 19 changes that element to 19. After making this change, if we look at age again, we'll see the updated vector. Understanding how to access and modify vector elements is crucial because it allows us to manipulate our data precisely, which is essential for accurate analysis and insights. Let's take a closer look at data analysis in R here. We see how we can create a data frame using the student's data, including their names, ages, and marks. Notice that the command student's data, frame, name, age, marks 1, marks 2, helps us organize related vectors into a single structure. When we print students, it displays all this information neatly formatted. We also have profile data, which initially includes just the names, and then we add ages to it with profile data, frame, name, age. This shows how we can modify or expand our data frames as needed. Additionally, there's a line where we try to combine name, age, and marks into students 1 using C. But that's not the right way to do it for data frames. It's more for vectors. Now the SDR function is highlighted here, It's a very important feature in R because it quickly shows the structure of your data frame, including types and dimensions. This is especially useful when importing data from external sources, which is very common in data analysis. Most of the time, when data is imported from outside sources, it's stored as a data frame. Understanding how R handles data frames is key, because they allow us to organize and analyze related data efficiently. So, in summary, data frames are fundamental in R for managing and analyzing datasets, especially when working with imported data. They're powerful, flexible, and essential to your data analysis toolkit. Alright, let's dive into accessing data in R data frames. On this slide, we're looking at different ways to select and extract data from a data frame called students. For example, Students 1 retrieves the first row, which is useful when you want to see or work with a specific record. Similarly, Students 1 gets the first column across all rows, often used to extract a particular variable like student IDs or names. If you want to select a specific set of columns, you can use Students 2, 4, which grabs columns 2 through 4. Alternatively, Students -1 means all columns except the first one. These techniques give you flexible ways to access parts of your data frame based on your analysis needs. Next, if you want to exclude a row, you can use Students -1, which removes the first row and keeps the rest. This is handy when you want to omit a specific entry or outlier. Moving on to column access, you can use the $sign notation, like Students' $name or Students' $marks1, to directly access those specific columns. It's a convenient and readable way to work with individual variables. You can also use the bracket notation with column names, such as Students' marks2 or Students' name. Both methods are valid and allow you to select columns by name, which is especially useful when you have many variables or want to write more descriptive code. Overall, these techniques are essential for efficiently working with data frames in R, enabling you to select, exclude, or focus on specific parts of your dataset as you analyze and interpret your data. Alright, let's look at slide 29. Here, we're diving into data access in R with a simple example. We've got 3 different ways of accessing data from a data frame called students. First, we assign students' $name to X. This extracts the name column as a vector. Next, Y is assigned students' name, which also retrieves the name column, but notice it returns a data frame instead of a vector. Then Z is assigned Students 1, which fetches the first column, again as a data frame. When we look at X and Y, and then check their structure with SDR, X and SDR, Y, you'll see that is a vector, whereas Y remains a data frame. This highlights an important point. Even though all 3 methods access the same data, they can produce different types of results. This difference in how data is accessed can influence how you work with your data later on. Understanding whether you're dealing with a vector or a data frame is key to applying the right functions and avoiding unexpected errors. This is fundamental as we move forward in analyzing data efficiently and accurately. Welcome to slide 30 of the data analysis course. Here, we're exploring lists in R. First, we define some objects. X is a vector from 1 to 20, Y is a logical false, Z is a character string Mike, K is the number 30, and L represents a variable called students. We also create a description string, disk, which says this is a list of all my R elements. Next, we use the SDR function to examine the structure of each object. X, Y, Z, K, and L. This helps us understand their internal structure, types, and contents. Then, we combine all these objects into a list called mylist using the list function. This is a key concept. A list is essentially a collection of R objects or components. Lists are incredibly flexible because they allow us to gather a variety of objects, even if they are of different types or lengths, under a single name. This makes data organization much easier, especially when dealing with complex or diverse datasets. Remember, creating a list is straightforward. Just use list. The important takeaway is that lists are versatile containers, enabling us to manage multiple related or unrelated objects efficiently within our analysis workflow. Now let's take a look at slide 31, which is all about accessing lists in Python. Here, you see the command str_mylist. This is used to convert the list into a string, which can be helpful for displaying or printing. Next, we have mylist itself, which simply refers to the entire list. When we want to access individual elements within the list, we use indexing. For example, mylist1 retrieves the second item, since Python uses zero-based indexing, and mylist2 gets the third item. Understanding how to access list elements is fundamental because it allows us to manipulate and retrieve data efficiently. Remember, when working with lists, always keep in mind the index positions. This concept ties into the overall theme of data analysis. Being able to organize and access your data quickly and effectively is key to making meaningful insights. Now, let's look at how users can manage their command history more effectively. On this slide, we see that the user has the option to send the selected history either to the console or directly to the source. This is particularly useful because it allows quick access to commands you've previously executed, making your workflow more efficient. For example, if you want to review or reuse a command, you can choose to send it straight to the console for immediate use, or send it to the source for editing or further analysis. This flexibility enhances your ability to analyze and work with your command history seamlessly. It's a simple yet powerful feature that helps streamline data analysis tasks, especially when working with complex or repetitive commands. Remember, this capability is all about making your command management more accessible and efficient. Now, let's talk about R scripts or code files. These are essentially files where you store your R commands and code. They are really useful because you can re-execute the stored codes whenever you need to, which saves a lot of time and effort. To run the commands in your script, all you need to do is hit Ctrl+Enter, and R will execute the selected line or the code chunk. It's also important to save your R script files for future use. This way, you can revisit your analysis, make adjustments, or share your work with others easily. Remember, keeping well-organized scripts is key to efficient data analysis. Throughout this course, we emphasize the importance of scripting, as it helps maintain reproducibility and clarity in your work. So, mastering how to write, save, and run R scripts is a fundamental skill you'll carry forward in your data analysis journey. Today, I want to talk about saving R scripts, which is a crucial part of our data analysis workflow. When you're working in R, saving your script ensures that all your code is preserved exactly as you've written it. This way, you can come back to it later, make updates, or share it with others. Saving your script also helps in maintaining a clean and organized project. Remember, the most important concept here is to save frequently and properly, so you don't lose your work. This step connects to the overall theme of efficient and reproducible data analysis, making sure your work is safe and easy to revisit whenever needed. So, when we talk about saving all the R objects, it's important to remember that this includes not just simple variables, but also lists, arrays, and data frames. Essentially, everything you've been working on in your session can be stored. This is especially useful if you've done a lot of data manipulation or analysis and want to preserve your current state. By saving these objects, you can load them later to pick up right where you left off, without needing to redo all the work. It's like creating a snapshot of your current environment, your working image, that you can reload whenever you need. This process saves time and ensures consistency, especially when you're working on complex projects or sharing your work with others. So remember, saving your R workspace is a crucial step for efficient and effective data analysis workflows. In this slide, we're walking through the basics of creating and organizing data in R first. We create a vector called income data for 4 employees, with values of 5,500, 6,700, 8,970, and 5,634. This represents their individual salaries. Next, we introduce a new variable called tax and assign it a value of 0.2, which we'll use to calculate net income after tax deductions. We also create a variable for the year, saving 2015, and a variable for the company, saving HP for Hewlett-Packard. Then, we derive the net income by deducting the tax from each employee's income, essentially multiplying the income by one tax. Moving forward, we create a vector for employee names, Red, Ken, Finn, and Scott. Using these, we make a data frame that combines employee names with their net incomes, giving us a clear and organized view of the data. Finally, we compile all this information, the company name, year, tax rate, employee names, and salary data, into a list. This process forms the foundation of our first R program, which is crucial for data analysis. The key takeaway here is understanding how to create, manipulate, and organize data in R, which is essential for any data analysis task. Alright, on this slide, I want to walk you through a simple example of a basic data analysis in R here. We're defining some income data for a few individuals with the line income C, 5,500, 6,700, 8,970, 5,634. This creates a numeric vector of incomes. Next, we set a tax rate of 20% with tax 0.2, which we'll use to calculate net income. We also specify the year as 2015, and the company as HP for context. The key point here is how we calculate net income by multiplying each income value by one tax. So, net income, one tax. This simple calculation adjusts the gross income to reflect what remains after taxes. We then create a small employee database with their names, emp name C, Red, Ken, Finn, Scott. Using this, we assemble a data frame called emp database that combines the net income and employee names. This is a fundamental step in data analysis, organizing related data into a structured format, making it easier to analyze. Finally, I put all these pieces into a list called empdb list, which contains the original incomes, tax rate, year, company, and the employee database. The main takeaway here is how these basic R commands come together to create a simple data analysis workflow, defining data, performing calculations, organizing information into data frames, and packaging everything into a list. This foundational skill is essential for more complex analyses, and it connects to the overall theme of learning how to manipulate and analyze data efficiently with R. Let's take a closer look at some of the key numeric functions we use in R first. We have the absolute value function, abs, x, which simply returns the non-negative value of a number. For example, if you input -5, abs -5 gives you 5. Next is the square root function, sqrt, x, which calculates the square root of a number. So, sqrt, 9 equals 3. Moving on, we have several functions that help us round numbers. The ceiling, x, function rounds a number up to the nearest whole number, so ceiling 3. 475 gives us 4, while the floor x function rounds down, making floor 3, 475 equal to 3. The trunk x function, on the other hand, simply cuts off the decimal part without rounding, so trunk 5, 99 results in 5. For more precise rounding, we use round x, digits equals n, where we specify the number of decimal places. For example, round 3, 475 digits equals 2 gives us 3.48. There's also the signif x, digits equals n function, which adjusts the number to a specified number of significant digits. So signif 3, 475 digits equals 2 results in 3.5. Now, beyond these basic functions, R offers a suite of mathematical functions like acos x, cosh x, akash x, and others, which are essential for more advanced calculations. We also have functions for logarithms, log x for natural logarithm and log 10 x for common logarithm. To exponentiate numbers, we use exp(x), which computes e raised to the power of x. All these functions form a vital part of our data analysis toolkit, helping us manipulate and interpret data accurately and efficiently. Welcome to the data analysis course. Today, I'll walk you through some essential numeric functions in R here. We start with y assign the value of the absolute of -20, so y becomes 20. Next, we define as the sum of y plus 5, which results in 20 plus 5, giving us 25. Then, we take the logarithm of x and store it in z. Remember, The log function computes the natural logarithm, which is useful for many data transformations. Finally, we round z to 1 decimal place to make the result more readable. This demo showcases how these basic numeric functions can be combined to manipulate and analyze data efficiently. Understanding these functions is fundamental as they form the building blocks for more complex data analysis tasks. Let's take a closer look at some essential character functions in R that are vital for data analysis. First up is the subster function, which allows us to extract or replace parts of a character string. For example, if we have the string objdef and use subster x24, it returns bcd. If we want to replace those characters, we can assign a new value like subster x24 22,222, which transforms the string into a 222f. Next, we have the grep function, which is powerful for searching patterns within character vectors. It looks for a pattern, and if ignore case is set to false, it's case sensitive. When fixed equals false, it interprets the pattern as a regular expression, giving us flexible search capabilities. For instance, grep AC, B, A, C, fixed equals true will return 2, indicating that A is at the second position in the vector. Then there's the sub function, useful for finding a pattern and replacing it with specified text. If fixed equals false, it treats the pattern as a regular expression. For example, sub \s there replaces the first space with a dot, resulting in hello there. We also have strsplit, which splits strings based on a specified delimiter. For example, strsplit ABC splits the string into individual characters A, B, and C. The paste function helps us concatenate strings with the sep parameter controlling what separates them. For example, paste x13 sep equals will produce x1, x2, x3. If we change sep to m, then paste x13 sep equals m creates xm1, xm2, xm3. Finally, there's tuple, which converts strings to uppercase, making it easier to standardize text data for analysis. These functions collectively enhance our ability to manipulate and analyze character data efficiently, tying into the overall theme of effective data wrangling in R. Welcome to Slide 40, one of our data analysis course. Today, we'll look at some fundamental character functions in R, which are essential for manipulating and understanding text data. Let's start with an example. We have a customer ID, which is stored as cust ID and is equal to cust 1,233,416. First, I want to show you how to extract a part of this string. Using the subster function, we can select specific characters. For example, subster cust ID 510 extracts characters from position 5 to 10. This is useful when you need to isolate certain parts of a string, like a code or a segment of an ID. Next, I'll demonstrate how to convert the entire string to uppercase. The tuple function takes the cust ID and transforms all its characters to uppercase, making it easier to standardize text data for comparison or analysis. Finally, I want to introduce the concept of demonstrating these character functions in action. This helps us understand how to manipulate string data efficiently, which is a crucial skill in data analysis workflows. As we progress through this course, you'll see how these simple functions serve as building blocks for more complex data transformations. Remember, mastering character functions allows you to clean, prepare, and analyze text data more effectively. Let's take a look at some essential resources for our data analysis course. We've got several key texts that can really deepen your understanding of R and its applications. For instance, P. Kunert and B. Venable's book, An Introduction to R, is a foundational resource that covers software for statistical modeling and computing. It's great for building a solid base. Then there's J.H. Maindonald's Using R for Data Analysis and Graphics, which emphasizes practical data analysis and visualization techniques. B. Munchen's R for SAS and SPSS users is particularly helpful if you're transitioning from those platforms. It's tailored to help you adapt your skills. W.J. Owens, the R Guide offers a comprehensive overview of R's capabilities, making it a handy quick reference. D. Rossiter's Introduction to the R Project for Statistical Computing, designed for use at the ITC, provides insights into R's core features and its application in academic settings. And finally, W.N. Venables and D.M. Smith's book, An Introduction to R, is another excellent resource for beginners. Now, a crucial point to remember. As you work through exercises, you might come across new commands. If you're curious about what a command does, always consult the documentation. R doesn't list all commands in one place, so reading the help files is the best way to learn. I encourage you to practice this. Getting comfortable with reading documentation is a vital skill in mastering R. Moving on to the tutorials. These are all in PDF format and designed to reinforce your learning. They serve as practical guides to applying what you've learned. And finally, there's the R Help resource, which is an invaluable support tool whenever you need quick assistance or clarification. Remember, familiarizing yourself with these resources will greatly enhance your confidence and proficiency in data analysis with R. Today, I want to highlight some fantastic resources for mastering data analysis with R. First up is Venkat Reddy, who offers comprehensive courses that cover the core concepts and practical applications. Then, there's Paul Jaisler's excellent R tutorial, which is a great starting point for beginners wanting to get comfortable with R syntax and basic data manipulation. We also have Dave Roberts' outstanding labs on ecological analysis, which are particularly useful if you're working with ecological data or environmental datasets. Additionally, David Rossiter provides excellent tutorials that delve into nearly every aspect of R, making complex topics more accessible. A special mention goes to Rob Kabikoff, whose notes follow a web page format that many find very helpful for structured learning. Another valuable resource is Vincent Zunikin's Introduction to R, which is perfect for those just starting out. The R Cookbook is also a fantastic reference for quick solutions and practical tips. Finally, the Data Manipulation Reference and R tutorials are essential for deepening your understanding and improving your skills. Connecting all these points, what's important to remember is that these resources collectively provide a solid foundation for anyone serious about data analysis in R, whether you're a beginner or looking to deepen your expertise. They support the overall theme of building a strong, practical skill set in data analysis. Now, let's move on to step 2, which is data handling in R. This step is crucial because how we manage and manipulate our data directly impacts the quality of our analysis. In R, data handling involves several key processes, such as importing data from various sources, cleaning it to remove errors or inconsistencies, and transforming it into a suitable format for analysis. We often start by reading datasets using functions like read, CSV, or read table, which allow us to bring in data from CSV files or other formats. Once the data is loaded, cleaning is essential, checking for missing values, duplicates, or outliers, and then deciding how to handle them. Transformations might include filtering data, creating new variables, or reshaping data structures to better suit our analytical needs. Throughout this process, it's important to keep the overall goal in mind, ensuring our data is accurate, consistent, and ready for meaningful analysis. Remember, effective data handling is the foundation for deriving reliable insights from your data. Welcome to slide 45 of our data analysis course. Today, we'll focus on data handling in R, a crucial step in our analysis workflow. We start with importing data from various external files such as CSV, TXT, SAS, and Excel formats. Each of these file types has its own specific methods for importing into R, but the key idea is to understand how to bring data from outside sources into our environment efficiently. Once our data is in R, we often need to work with datasets, creating new variables as needed to enhance our analysis. This could involve transforming existing data or deriving new insights. Data manipulation is fundamental, and R provides powerful functions to do this smoothly, whether it's filtering, transforming, or summarizing data. Sorting data is another vital task. Sorting helps us organize our data for better visualization and analysis, and removing duplicates ensures our data is clean and reliable. These steps are essential for maintaining data integrity before any modeling or reporting. Exporting datasets back into external files is equally important. Whether you want to share your results or use them elsewhere, R makes it simple to export datasets in formats like CSV or TXT. Finally, data merging allows us to combine different datasets based on common identifiers, enriching our analysis by integrating multiple sources. This slide summarizes the core activities involved in data handling within R: importing, creating variables, manipulating, sorting, exporting, and merging. Mastering these steps will streamline your workflow and improve the quality of your analyses. Welcome to slide 46 of our data analysis course. Today, we'll be talking about importing data. Importing data is a fundamental step in data analysis because it allows us to bring data from various sources into our analysis environment. Whether you're working with Excel files, CSVs, or databases, understanding how to import data efficiently is crucial. The key points here are that the process may vary depending on the data source and the tools you're using. For example, in Python, we might use pandas read CSV or read Excel functions, while in other software, there might be specific menus or commands. It's also important to ensure that the data is correctly imported. Checking for any formatting issues or missing values right after import can save you a lot of trouble later on. Remember, clean and well-structured data is the foundation of accurate analysis. Connecting this to our overall theme, importing data correctly sets the stage for all the subsequent analysis steps. The better you handle this initial step, the smoother your entire project will go. So, mastering data import techniques is essential for efficient and reliable data analysis. Now let's look at slide 47, which focuses on data importing using the GUI option. As you can see, the slide is numbered 3, indicating that this is part of a sequence in the course. The main point here is that importing data can be done easily through the graphical user interface, or GUI, which is very user-friendly. Using the GUI option allows you to avoid complex coding and makes the data import process much more accessible, especially if you're just starting out. It provides a visual way to navigate through your files, select the data you want to analyze, and import it directly into your workspace. This method is particularly important because it streamlines the workflow, saving you time and reducing errors that can happen with manual coding. Connecting this to our overall theme of data analysis, mastering simple yet powerful tools like the GUI enhances efficiency and helps you focus more on deriving insights rather than technical hurdles. So remember, whenever you're working with new data sets, exploring the GUI options available can make your data importing process smoother and more intuitive. Today, we're focusing on how to import CSV files using R, which is a fundamental step in data analysis. On this slide, you can see a couple of examples of R code for importing data. First, there's the command R file name, read, CSV, full path with extension. What this does is tell R to read in a CSV file from a specified location on your system and store that data into a variable named R file name. Next, we have an example where we're importing a dataset called Sales by Country V1. Notice how the path includes the folder structure, like datasets, Superstore sales data, and then the file name itself. This illustrates how you can organize and access your datasets efficiently. The key point here is that reading CSV files in R is straightforward with the read CSV function. It's a versatile way to load your data into R for analysis. Understanding the file path is crucial. It needs to be accurate for R to locate and load your data successfully. This step is essential because, without importing your data properly, you can't perform any meaningful analysis or visualization later on. So, mastering this simple yet powerful command helps you streamline your workflow and lays the foundation for all your data analysis tasks. Now, let's look at how we import different types of data files in our data analysis course. I'll be guiding you through some practical examples. First, we'll import the car's data from a CSV file using the GUI, so you'll see how straightforward it is to bring in structured data this way. Next, we'll switch to using code to import healthcare data, highlighting the flexibility of coding methods. Then, we'll import survey data from a TXT file through the GUI again, which is useful for quick, manual imports. You'll notice that sometimes, when importing other files like the client manager, TXT, the code may vary slightly or require adjustments, so I'll point out whether there are any changes needed in the code for different file types. This hands-on lab on importing data is designed to reinforce key concepts, whether you're using GUI or coding techniques, and emphasize how to efficiently bring diverse datasets into your analysis environment. Connecting these points to the overall theme, understanding how to import data properly is fundamental to successful data analysis, as it sets the foundation for all subsequent analysis steps. Let's move on to the next important aspect of data analysis in SAS. When working with SAS datasets in R, you often need a specific package called SAS7BDAT. If you don't have it installed yet, you can simply run install packages SAS7BDAT. Once installed, load the package into your session using library SAS7BDAT. Now, to read a SAS dataset, you use the read SAS7BDAT function. For example, if your dataset is located at a specific path on your computer, just specify that path within the function. In this case, we're importing a file called GNP SAS7BDAT from a directory on my computer. After importing, I like to view the data by using the view function, which opens the dataset in a spreadsheet-like view. The key takeaway here is that importing SAS files into R is quite straightforward once you have the right package and know the path to your dataset. This step is crucial for analyzing SAS data efficiently within R and connecting your SAS datasets with your broader data analysis workflows. Welcome to slide 51 of our data analysis course. Today, we'll focus on importing data, which is a fundamental step in any analysis. I'll show you how to import GNP data from SAS sample datasets, a common source for economic data. We'll also look at importing demographics data, which provides valuable context for understanding various populations. During the lab, we'll practice these import techniques, emphasizing how to efficiently bring data into our environment for analysis. Remember, getting your data correctly loaded is crucial because it sets the foundation for accurate insights later on. By mastering these import processes, you'll be better equipped to handle different datasets and integrate them seamlessly into your workflow. This step is essential to connect raw data with meaningful analysis, which is at the heart of our overall course theme. So, let's dive into these practical examples and get comfortable with the import procedures. Let's talk about importing Excel files in our data analysis course. To begin, sometimes you need to install a package to handle Excel files smoothly. In this case, we use install packages XLSX. Once installed, you load the library with library XLSX. This package provides functions that make working with Excel files straightforward. Now, to read an Excel file, you can use the command dataset read XLSX C/myExcel XLSX sheet name equals misheet. Here, you specify the file path and the sheet name you want to import. This is a powerful way to bring external data into R for analysis. Remember, handling data efficiently is key in data analysis, and importing files correctly is the starting point. So, always ensure your file paths are correct and your sheet names match exactly. This process helps you seamlessly integrate your Excel data into your R environment, making your workflow much smoother. Let's talk about importing data from Excel into R first. The ODBC connection method works only on 32-bit Windows systems, so it's limited in that sense. Next, there's the XLS read-write package, but it doesn't support newer XLSX files, which can be a bit restrictive. The XL Connect package is another option, but it requires Java to be installed and configured properly. Similarly, the XLSX package also needs Java, which can sometimes complicate setup. there's also a self-made function I want to highlight, which I got from a GitHub gist. You can source it directly from the URL and then use it for importing your XLSX files like XLSX to R, myfil. XLSX, header equals true. Overall, there are many ways to import data from Excel, and choosing the right method depends on your system setup and the type of files you're working with. It's good to be aware of these options so you can select the most efficient approach for your analysis. Now let's take a look at how we connect to a database using R, specifically through the RODBC package. On this slide, you can see the basic steps involved in establishing a connection, executing queries, and then closing that connection. First, we load the library with library, ROD. Then, we create a connection object using ODBConnect, where we specify the data source name, or DBLink in this case, along with the user ID and password. Once connected, we can fetch data directly into R using SQL Fetch, which pulls entire tables here. We're bringing in the sales data. Alternatively, for more specific data, we can use SQL Query to run custom SQL commands, like selecting all records from the orders table. After we've retrieved our data, it's important to close the connection with close, con, to free up resources. This process is fundamental because connecting to databases allows us to access large datasets efficiently, which is crucial for data analysis. Throughout our course, understanding how to establish these connections will empower you to work seamlessly with real-world data stored in various databases, making your analyses more robust and dynamic. Today, we'll be focusing on working with datasets, which is a fundamental part of data analysis. When you're dealing with datasets, it's important to understand how to handle, explore, and manipulate the data effectively. This involves cleaning the data, identifying any inconsistencies, and making sure it's in a suitable format for analysis. Remember, the quality of your insights depends heavily on the quality of your data. We'll also look at different methods to explore datasets, such as summarizing key statistics and visualizing data distributions. These steps help you spot patterns, trends, or anomalies early on. Connecting these concepts to our overall theme, working skillfully with datasets empowers us to derive meaningful insights and make informed decisions based on real data. So, mastering these techniques is essential for any successful data analysis project. Let's start by examining the levels of the region variable in our demographics dataset. This helps us understand the different categories or groups present in the data. Moving on, I want to highlight the data analysis course, which Venkat Reddy is leading, emphasizing the importance of these foundational skills. Now, to get a sense of what objects are loaded in our R environment, we use the ls function. This shows us all the objects we have in memory. When we want to understand the structure of our data, the names function helps us identify the column names in the GNP data dataset. Next, to see the overall size of our dataset, we use dim, which gives us the number of rows and columns, crucial for understanding the scale of our data. To get a quick preview of the actual data, the head function shows us the first few observations, and here I've included both GNP data and the first 20 rows of demographics to compare. Similarly, if we want to look at the tail end of our data, the tail function does that, and specifying n equals 10 shows us the last 10 observations, useful for checking the most recent data points. For a more detailed understanding of the dataset structure, such as data types and how the data is organized, we use SDR. This gives us a complete overview. Lastly, when working with categorical variables, understanding their levels helps us see the different categories or groups within that variable, which is key for accurate analysis. All of these tools, viewing data, checking structure, and understanding categories, are essential for effectively analyzing and interpreting our data as part of the overall data analysis process. Let's start by looking at how we handle data in R first. We create a new dataset called new, which is simply the head of GNP data, so we get the first few rows. Then, we remove that new variable from our workspace to keep things clean. Next, I want to show you how to understand the structure of our data. Using SDR demographics $region, we can see what type of variable region is, whether it's a factor, character, or numeric. Similarly, SDR demographics $pop gives us insight into the population variable. To get a quick look at the data itself, we just print the entire demographics dataset. And if we want to view it more interactively, we can use View Demographics, which opens it in a separate window, making it easier to explore and analyze. Now moving on to summaries. The Summary Demographics command provides us with a quick statistical overview of all variables, like minimum, maximum, median, and quartiles, helping us understand the distribution at a glance. For a more detailed description, especially with complex or large datasets, the describe GNP data function from the HMISC package is very useful. Just remember, if you haven't installed HMISC yet, you'll need to run install packages HMISC first. Finally, once we're done exploring, we can remove the dataset from our environment to free up memory, ensuring our workspace stays organized and efficient. All these steps, viewing structure, printing, summarizing, are essential for understanding your data thoroughly before diving into analysis or modeling. Now let's move on to some practical data analysis steps. First, we'll import the data from the file named Petrol Consumption by City, CSV. Once we've loaded it, the next step is to understand the dataset size, so we'll check how many rows and columns it contains. This gives us an idea of the dataset's scope and complexity. Then, we'll look at the column names to understand what variables we're dealing with. It helps us get a quick overview of the data structure. After that, I'll show you how to print the first 10 observations so you can see the initial part of the data. Similarly, we'll look at the last 5 observations to get a sense of how the data ends. Next, we'll generate a summary of the dataset, which includes descriptive statistics like mean, median, and quartiles. This helps us grasp the distribution and central tendencies of the data. We'll also print the structure of the data, which gives us detailed information about data types and how each variable is stored. Focusing on the petrol consumption field specifically, we'll describe its characteristics, like its range, average, and variability. To practice working with data subsets, we'll create a new dataset containing only the first 30 observations. I'll show you how to print this subset, giving you a glimpse into working with smaller chunks of data. Then, we'll remove this temporary dataset to keep our workspace clean. Finally, this slide is part of a lab exercise where you'll practice printing data and meta information, reinforcing the concepts we've covered. This hands-on approach helps solidify your understanding of data inspection and manipulation in analysis workflows. Welcome to this part of the data analysis course. I'm Venkat Reddy, and today we'll talk about manually editing data in R. On this slide, you see the command New Data Edit, GNP data. This command opens up a spreadsheet-like interface where you can directly modify your data. After making your changes, you can view the first few rows with the head New Data command to check your updates. The key point here is that manual editing allows you to correct errors or make adjustments that might be easier to do interactively rather than through code. It's a powerful feature, especially when working with small datasets or making quick corrections. Connecting this to our overall theme, manual editing in R provides flexibility and control, making your data cleaning process more efficient and accurate. Just remember to be cautious. Manual edits can introduce errors if not carefully reviewed, so always double-check your changes. In this slide, we're diving into how we can create new datasets by selecting specific parts of our original data. First, I want to show you how to select a range of rows. For example, Petrol 1 contains rows 5 through 20. This is useful when you want to focus on a particular segment of your data. Next, we look at selecting specific rows by their indices, like Petrol 2, which includes only rows 5, 10, and 20. This approach is helpful when you're interested in particular data points. Moving on to columns, Petrol 3 demonstrates how to keep certain columns, specifically columns 2 to 4. This helps us narrow down our dataset to the variables we care about. Similarly, Petrol 4 shows how to select specific columns by their names, like city index and consume mil gallons, making our dataset more relevant to our analysis. We can also combine row and column selection, as seen with Petrol 5, where we keep rows 5 to 20 and only columns 1, 3, and 5. This is especially useful when you want a focused subset of data for detailed analysis. Lastly, Petrol 6 illustrates how to exclude certain columns, such as columns 3, 5, and 6, while keeping the rest. This is an efficient way to remove unnecessary information from your dataset. Overall, these techniques of subsetting, whether by rows, columns, or both, are fundamental tools in data analysis, allowing us to tailor our datasets precisely to our needs and make our analysis more efficient and targeted. Welcome to this part of the data analysis course. Today, we'll be working with the Market Data 1 CSV file. The goal here is to create new datasets based on specific filters. First, we'll select the first 40 market campaigns only. This helps us focus on a manageable subset for detailed analysis. Next, we'll narrow down our data to only include the campaign name, start date, and end date, which are crucial for understanding campaign timelines. Then, we'll move on to selecting between 700 and 1,000 observations, but only keeping 4 key variables: ID, name, budget, and reach. This allows us to analyze the core metrics of these campaigns without too much clutter. Lastly, we'll look at a larger chunk, between 5,000 and 6,000 observations, but this time, we'll drop the budget and reach fields. This might be useful for certain types of exploratory analysis or data cleaning exercises. Throughout this lab, we're practicing subsetting data, which is a fundamental skill in data analysis. It helps us focus on relevant portions of data, making our analysis more efficient and effective. Remember, the key is to understand why we're filtering and how it aligns with our overall analysis goals. All right, in this slide, we're diving into how to select data with conditions on variables in R, for example. If we want to filter complaints where the budget exceeds $5,000, we use the subset function. The syntax looks like this: new data subset, old data, condition. You can combine conditions using logical operators like for OR and for AND. For instance, if we want to select market data where the budget is greater than 5,000 and the number of assets is more than 10, we write market 1 subset, market, budget 5,000 and num assets 10. Similarly, if we're interested in data where the budget exceeds 10,000 or the number of assets is over 10, we'd write market 2 subset, market, budget 10,000, num assets 10. The key takeaway here is that subsetting data with variable filters allows us to focus our analysis on specific segments that meet our criteria, making our insights more targeted and meaningful. This is a fundamental skill in data analysis, helping us refine our datasets based on multiple conditions efficiently. Now, let's look at how we can apply AND, OR conditions along with numeric and character filters in data subsetting. In this example, we're creating a new subset called Market 3. Here, we're selecting data where the budget is greater than 10,000 or the number of assets is more than 10. And at the same time, the vertical is business finance. This demonstrates how logical operators can be combined to filter data based on multiple conditions. Moving on, we have Market 4, where we add an extra layer of specificity. We're not only applying the same combined conditions, but we're also selecting specific fields, name, start date, end date, and vertical, that we want to include in our subset. This helps us focus on relevant data points and makes our analysis more efficient. Overall, these examples show how subsetting with variable filter conditions allows us to extract precisely the data we need, based on complex criteria, which is a powerful tool in data analysis. By mastering these techniques, we can handle more sophisticated filtering and gain better insights. Now, let's look at how we can work with the cars CSV data to create specific subsets. First, we're importing the dataset into our environment. Then, we create a new dataset that includes only Audi cars by filtering where the make is equal to Audi. This helps us focus on a particular brand. Next, we create another dataset that captures all cars with horsepower greater than 300 and more than 6 cylinders. This allows us to analyze high-performance vehicles with specific engine features. Moving on, we generate a dataset that contains only SUV cars, but we keep just 4 variables: make, model, type, and MSRP. This simplifies our data for targeted analysis. Similarly, we create a subset that includes only cars from Audi, BMW, or Ford. Again, we limit the variables to make, model, type, and MSRP to streamline our focus. This slide is part of our lab on subsetting data using variable filter conditions, which is a crucial skill in data analysis. It helps us extract meaningful information tailored to our specific questions. So, by mastering these techniques, you're better equipped to handle diverse data scenarios and extract insights effectively. Today, I'm going to talk about creating calculated variables in R. This is a crucial skill in data analysis, because often we need to generate new variables based on existing data to uncover insights or simplify our models. Creating calculated variables allows us to transform data, combine information, or derive new metrics that are more meaningful for our analysis. In R, we typically do this using simple operations or functions, and it's quite straightforward once you get the hang of it. We'll look at some examples, such as creating a new variable like BMI from height and weight, or categorizing data based on certain conditions. Understanding how to efficiently create these calculated variables is key to making your data work harder for you and improving the quality of your analysis. So, let's dive into some practical techniques for doing this in R. On this slide, we're focusing on how to work with data in R, specifically within a data analysis course. First, I want to show you how to access a variable directly from a data frame. For example, if you type demographics $name, R will print out the name variable. But it's important to remember that trying to access a variable using just the name, like directly typing female sculpt, doesn't work here because R doesn't recognize it outside the context of the data frame. If you try to do that, you'll get an error saying object female sculpt not found. To make things easier, we can attach the data frame to our R environment using the attach function. Once attached, we can directly call the variable like female sculpt without the $sign. However, it's crucial to remember to detach the data frame after we're done. Leaving data attached can cause confusion or conflicts later, especially if we work with other datasets. So, after our operations, we detach the data frame with detach demographics. This process of attaching and detaching data is a handy way to simplify variable access during analysis, but always be cautious and remember to detach when finished. This way, we keep our workspace clean and avoid potential issues. This concept ties into our overall theme of efficient and organized data management in R for data analysis. Let's talk about how we create new variables in R using the assignment operator. This is a key concept because it allows us to add calculated fields to our datasets. For example, if we want to add a new column called sum that adds x1 and x2, we write dataset $sum dataset $x1 plus dataset $x2. Similarly, to get the mean of these two variables, we can do dataset $mean, dataset $x1 plus dataset $x2/2. Now, there's also a way to work with variables directly in the current environment by using the attach function. When we run attach dataset, R makes the variables x1 and x2 accessible without having to specify the dataset each time. So we can write dataset $sum x1 plus x2, and it works because R now knows to look in the attached dataset. Similarly, for the mean, we write dataset $mean x1 plus x2/2. Once we're done, it's important to detach the dataset with detach dataset. This keeps our workspace clean and prevents any confusion or errors later on. Overall, understanding how to create calculated fields in R, either by referencing the dataset directly or by attaching it, is essential for efficient data analysis. This technique allows us to add meaningful derived variables that can help us interpret and visualize our data more effectively. Welcome to this part of the data analysis course. I'm Venkat Reddy, and today we'll be exploring calculated fields in R using the CARS dataset. First, Let's look at how we can create a new variable, such as cars $HW ratio, by dividing horsepower by weight. This is a straightforward example of creating a new feature based on existing data. Next, I'll demonstrate the use of attach. When we attach cars, R allows us to reference variables directly without the dataset prefix, which can make our code cleaner and easier to read. For example, after attaching, we can create a new variable lengthNew by multiplying length by 1.2. However, it's important to remember that creating new variables directly like lengthNew length 1.2 doesn't work without specifying the dataset name, because R doesn't know where to find length in that context. That's why attaching the dataset can be helpful temporarily for such operations. Afterwards, we detach cars to avoid confusion or conflicts later on, especially if we work with multiple datasets. In the next example, I show that to properly add a new variable to the dataset, we should assign it as cars $length new length 1.2, which explicitly updates the dataset itself. This is a good practice to keep our data organized and consistent. To sum up, this slide emphasizes how to create calculated fields in R, either by temporarily attaching the dataset for quick calculations or by explicitly assigning new variables back to the dataset. These techniques are essential for efficient data manipulation and making our analysis more dynamic. All right, let's talk about data analysis using some familiar concepts. Think of it like Excel, where you might use an if-then-else statement to make decisions. In R, we have a similar function called ifels. For example, you might create a new variable like this, newVar ifels, condition, true value, false value. It's a powerful way to assign values based on specific conditions. Take online sales, for instance. Suppose we want to categorize prices as high or low. If the list price is greater than 10,000, we label it as high, otherwise low. We do this with online sales $price ind ifels, list price 10,000, high, low. This technique is all about creating calculated fields efficiently. By applying if-then-else logic, we can generate new insights from raw data. It's a fundamental skill in data analysis because it helps us automate decision-making and simplify complex datasets. Remember, the key is understanding how conditions work and how to use them to derive meaningful categories or variables within your data. All right, let's walk through some key steps in our data analysis process. First, we import the AMS product sales CSV dataset. Once we have the data loaded, we create new variables based on specific conditions to help us analyze the data more effectively. For example, we calculate GDP-new by taking 90% of the real GDP value. This gives us a slightly adjusted figure that can be useful for more conservative estimates. Next, we compute the GDP rate by dividing the GDP by the total population, which helps us understand the relative economic size. We also need to estimate the unemployed population. To do this, we multiply the total population by the unemployment rate, but we need to be careful here. Since the unemployment rate is given in percentage, we should convert it into a decimal before multiplying. Finally, we create a new variable called target to classify sales performance. If sales are less than 700 million, we label it as missed. If sales fall between 700 million and 900 million, we call it reached. And anything above 900 million is categorized as exceeded. All of these calculated fields are essential in R for better data insight and are a good example of how we can manipulate data to answer specific business questions. This approach ties into our overall theme of leveraging data analysis to make informed decisions. Now let's look at some practical data manipulation techniques in R, specifically for our market data. First, we import the dataset named Market Data 1. Then, we create a new variable called nameNew, which takes the first 20 characters from the existing name variable. This helps us handle long names more efficiently. Next, we create another variable by converting the campaign name into uppercase, making it easier to compare or categorize later. Finally, we add a flag variable that takes the value 1 if the campaign's starting month is different from its ending month, and if they are the same. These kinds of calculated fields are essential for cleaning and preparing data for analysis. They allow us to extract meaningful insights and simplify complex information, which ties into our overall goal of effective data analysis. Welcome to this part of the data analysis course. Today, I'll be talking about sorting and handling duplicate records. These are fundamental steps in data cleaning and preparation. When we talk about sorting, it's all about arranging data in a logical order, either ascending or descending, so that patterns become clearer and analysis easier. It helps us find trends and outliers more efficiently. Handling duplicates is equally important because duplicates can skew our results or give us misleading insights. Identifying and removing duplicate records ensures our data is accurate and reliable. Remember, the goal here is to maintain data integrity so that our analysis reflects true patterns, not errors or repetitions. Both sorting and removing duplicates are crucial steps in the overall data analysis workflow, helping us prepare high-quality data for meaningful insights. All right, let's talk about data sorting in RSO. In our course, we often need to organize our data to make analysis easier. Here, we have a command like new data, old data order variables. By default, the order function sorts the data in ascending order, which is useful when you want to see your data from smallest to largest. Now, when working with online sales data, you might want to sort based on the list price. For example, online sales sort online sales order, online sales dollar list price will sort your sales data from the lowest to the highest price. But what if you want to sort in descending order? That's simple. Just add a minus sign before the variable, like online sales dollar list price. So, writing online sales sort one online sales order, online sales dollar list price will give you the data from the highest to the lowest price. You can also sort based on multiple variables. For instance, if you want to sort by price in descending order and then by average rating in ascending order, you can do that by specifying both in the order function. Online sales sort to online sales order, online sales dollar list price, online sales dollar av rating. This way, your data is organized exactly how you need it, whether by single or multiple variables, and whether in ascending or descending order. Sorting is a fundamental step because it helps reveal patterns and insights more clearly, which ties into our overall goal of effective data analysis. Now, in this part of the course, we're working with the customer attrition data from the import bank. I'll start by importing the dataset titled Bank Customer Attrition Data, CSV. Once that's loaded, the next step is to sort the data based on the customer's age. This helps us understand the distribution of ages within our customer base. We'll specifically sort the ages in descending order, meaning the oldest customers will appear at the top. Additionally, we'll sort the survey overall satisfaction percent in descending order as well. This way, we can easily identify which customers are most satisfied and see how satisfaction levels vary across different age groups. This sorting process is fundamental because it allows us to analyze the data more efficiently. By organizing it this way, we can quickly spot patterns or outliers that might be important for our overall analysis. This exercise is a great example of how data sorting helps us prepare for deeper insights, tying back to our theme of effective data analysis. Now, let's move on to the actual sorting in our lab activity, where you'll get hands-on practice with these steps. In this slide, we're focusing on identifying duplicates within our datasets using the duplicated function, which helps us find overall record-level duplicates. For example, when we run dupsonBill duplicated bill, it marks the records that are duplicates across the entire bill dataset. We can then generate a summary of these duplicates using the summary function and view the actual duplicate records with bill dupsonBill. Similarly, we do the same for the complaints dataset with dupson complaints, duplicated complaints, summarizing and examining the duplicates. Now, while record-level duplicates are useful, sometimes we need to identify duplicates based on specific key columns, like the delivery number. So, we check for duplicates in the bill dataset based on the del-no column with dupsonBill key duplicated, bill $del-no. Again, we can summarize and review these key-based duplicates. The same approach applies to the complaints dataset, where we look for duplicates based on complaints $DEL no. The key takeaway here is that identifying duplicates, whether at the record level or based on specific keys, is essential for cleaning our data and ensuring accuracy before analysis. This process helps us pinpoint redundancies and potential data quality issues, which is a critical step in any data analysis project. Now, let's talk about removing duplicates in our data analysis course. The simplest way to do this is by using the unique function. This function will consider only the unique records, making it easy to identify and filter out duplicates. For example, if I run unique on the bill dataset, it will return only the distinct entries. The same applies to the complaints dataset. When we want to remove duplicates based on specific variables, we add an exclamation mark before the duplicated function. This helps us identify which records are duplicates. For instance, by creating a logical vector like dupes in bill key, we can mark the duplicated entries in the bill's del no column. Running a summary on this logical vector gives us an overview of how many duplicates exist. Then, by subsetting the data with bill, dupes in bill key, we keep only the unique entries, effectively removing the duplicates. Finally, it's good practice to check the dimensions of our dataset before and after removing duplicates, so we can see exactly how many records were filtered out. This step ensures our data is clean and ready for accurate analysis. Removing duplicates is a crucial step in data cleaning, helping us maintain data quality as we proceed with our analysis. In this slide, we're focusing on data analysis techniques applied to telecom data, specifically TV commercial data, orders, and slots. The key tasks here involve importing the bill and complaints datasets, which are crucial for understanding customer issues and billing accuracy. Our first step is to identify duplicates across these datasets. Duplicates can distort our analysis, so it's essential to detect and handle them properly. We'll look for overall duplicates in both the bill data and the complaints data. Once we've identified these duplicates, the next step is to remove them based on the del no, which is a unique identifier for each transaction or complaint. By removing duplicates and saving only the unique records into separate datasets, bill unique and complaints unique, we ensure our data is clean and reliable. This process is fundamental because clean data leads to more accurate insights, which ultimately helps improve service quality and customer satisfaction. Remember, this hands-on practice of removing duplicates is a vital skill in data analysis, especially in telecom where large volumes of data are common. Today, I'll be talking about exporting data out of R, which is a crucial step in data analysis workflows. Once you've analyzed your data and generated insights, you often need to share or save your results, and that's where exporting comes in. We'll look at some of the key functions and best practices to ensure your data is exported accurately and efficiently. Remember, the goal is to make your data easy to access and interpret outside of R, whether for reporting, further analysis, or collaboration. So, let's explore how to do this seamlessly and effectively. Now, let's look at how we can export data from R into different formats. First, to export to a SAS dataset, we use the write foreign function, specifying the dataset and the file path, like C/dataset, SAS. This allows us to share data with SAS users seamlessly. Next, if we want to export to a tab-delimited text file, we use write table, where we specify the dataset, the file path such as C, //users //venc //documents //economic data, txt, and set sep equals /t to indicate tab separation. This format is useful for importing into many other applications and systems. For exporting to a CSV file, which is very common, we use write CSV, again specifying the dataset and the file path, like C, //users //venc //documents //economic data, CSV. CSV files are widely supported and easy to work with. If we prefer to export to an Excel spreadsheet, we need to load the XLS read-write library, and then we can use write XLS to save the dataset as an XLS file, such as This is handy when working with Excel-specific features or sharing data with users who prefer spreadsheets. Finally, to export data to SAS specifically, we load the foreign library and use functions like write foreign, which helps in exporting data in a format compatible with SAS. Overall, these methods give us flexibility to export our data into various formats depending on our analysis needs or the tools our colleagues are using. In this slide, we're focusing on exporting data from R, which is a crucial step in data analysis workflows. Here, I'm demonstrating how to save our sales data into external files using the write table function. First, we save it as a tab-separated text file, specifying the file path and setting sep equals \t to indicate tabs as separators. Then, we also export the same data as a CSV file, which is very common for sharing data across different applications. Notice how we change the separator to a comma with sep equals for the CSV. Exporting data allows us to store our results, share insights with others, or prepare data for further analysis in other tools. This process ties into the overall theme of data analysis, making sure our data is accessible beyond R, flexible, and ready for reporting or collaboration. Welcome to this part of the data analysis course. I am Venkat Reddy, and today we'll be discussing data sets merging and joining. These are essential techniques in data analysis because they allow us to combine information from different sources or tables. By merging and joining data, we can create a more comprehensive view and perform more sophisticated analyses. The key concept here is understanding the different types of joins, like inner, outer, left, and right joins, and knowing when to use each. For example, an inner join gives us only the matching data between two sets, while an outer join includes all data points, filling in gaps where there's no match. This process is crucial because real-world data often comes from multiple sources, and combining it correctly ensures our insights are accurate and meaningful. Throughout this section, I'll highlight how mastering merging and joining techniques is fundamental for effective data analysis, helping you work more efficiently and draw better conclusions from your data sets. Let's take a look at how we perform data merging in R on this slide. We see an example where we create a new dataset called new data by merging two data frames, DataOwn and DataTwo. The default method used here is an inner join, which means it only keeps the records that have matching keys in both datasets. When we specify the by argument with multiple keys, like by equals C, primary key 1, primary key 2, R will perform the join based on those two columns. This is useful when your data is linked through a composite key, meaning more than one column forms the unique identifier. Now, there are different types of joins you can perform. The inner join is the default, which is what we saw initially. If you want to include all records from both datasets, regardless of whether they match, you would use an outer join by setting all equals true. For a left outer join, which keeps all records from the first dataset and only matching ones from the second, you specify all, x equals true. Conversely, for a right outer join, which keeps all records from the second dataset, you set all, y equals true. It's important to understand these options because they determine how much data you retain when merging, especially when working with incomplete or partially overlapping datasets. And whether you're merging with a single primary key or composite keys, the syntax remains quite similar, just with the appropriate arguments. This merging syntax is a fundamental part of data analysis, enabling us to combine information from different sources efficiently and accurately. Let's take a closer look at some key data analysis techniques using R, specifically focusing on merging datasets. On this slide, we're working with two datasets, orders and slots. First, I load these datasets into R using the function. Now, the concept of merging or joining these datasets is crucial because it helps us analyze data from different sources together. Here, we have different types of joins. The first one is the union, which is represented by the newData1 variable. Using the merge function with all equals true, this performs a full outer join, meaning it combines all records from both datasets, matching where possible, and filling in missing values where there's no match. Next, we have the intersection, captured by new data 2. Here, by setting all equals false, we perform an inner join. This includes only the records that are common to both datasets, based on the specified keys. Then, we see examples of left and right joins, which are represented by new data 3 and new data 4. For new data 3, all, x equals true means it's a left join, keeping all records from the orders dataset and matching data from slots when available. Conversely, new data 4 uses all, y equals true, which is a right join, keeping all records from the slots dataset and matching orders data when possible. These different types of joins are fundamental for data analysis because they allow us to control precisely how datasets are combined, depending on whether we want to keep all data, only matching data, or focus on one dataset's completeness. Connecting this to our overall theme, understanding these joins helps us analyze TV commercial slots and orders more effectively, ensuring we can extract the insights we need from multiple data sources. Now let's move on to our data analysis process. First, we'll import the telecom bill and complaints data. Once we have that, the next step is to remove duplicates, which we'll do based on the DEL/NO or delivery number. This helps us ensure our data is clean and accurate. After cleaning, we'll create separate datasets for different scenarios. One dataset will include all customers who have either bill data or complaints data available. This way, we capture everyone who has some activity in our system. Then, we'll focus on customers who appear in both datasets, those who have both bill information and complaints. This is important because it lets us analyze relationships and patterns between billing and complaints. Next, we look at customers who have bill data along with any complaints they might have, if applicable. Similarly, we examine customers with complaints data along with their billing info, if they have any. Throughout this process, we're essentially performing data joins, merging different datasets based on common identifiers to get a comprehensive view. This is a critical step because it helps us understand customer behavior more holistically. This lab on data joins will give us practical experience in combining data sources effectively, which is a core skill in data analysis. Remember, the key here is to create meaningful datasets that allow us to analyze different customer segments and their interactions with our services. All right, now let's move on to step 3, which focuses on graphs, reporting, and analytics on R here. We're diving into how R can be used to create compelling visualizations, generate insightful reports, and perform advanced analytics. The key point to remember is that R offers a powerful suite of tools for transforming raw data into meaningful stories through graphs and charts. These visualizations are essential because they make complex data much easier to understand at a glance. Additionally, R's reporting capabilities allow us to automate the generation of reports, making the entire process more efficient and consistent. And when it comes to analytics, R provides a vast array of statistical and machine learning techniques to uncover patterns, trends, and insights that might not be immediately obvious. Connecting this to the overall theme, mastering these skills in R empowers us to communicate findings effectively, support data-driven decisions, and ultimately add value across various projects. So, in this step, we're really emphasizing the importance of visual and analytical tools in turning data into actionable knowledge. Now, let's move on to step 3, graphs, reporting, and analytics on R, which is a crucial part of our data analysis journey. In this section, we'll focus on how to visualize data effectively using graphs, generate insightful reports, and perform advanced analytics using R. These tools enable us to communicate our findings clearly and make data-driven decisions. We'll explore different types of graphs to suit various data scenarios, learn how to produce professional reports, and leverage R's powerful analytics capabilities. This step ties together all the concepts we've covered so far, helping us turn raw data into meaningful insights that can influence our strategies and actions. Today, we're diving into user-defined functions, an essential aspect of data analysis. These functions allow us to create custom operations tailored specifically to our needs, making our code more efficient and easier to manage. Instead of repeating the same steps over and over, we can define a function once and reuse it whenever necessary. This not only saves time, but also enhances readability and organization in our scripts. Remember, the power of user-defined functions lies in their flexibility. They help us handle complex tasks with simplicity. As we continue to explore data analysis techniques, mastering these functions will be a key skill that connects all the concepts we've discussed so far. Let's take a look at some simple data analysis concepts. Using R first, we'll find the squares of the first 20 numbers. I initialized a variable called square with a random value, and then used a loop to assign each position in the vector to the square of its index. This is a straightforward way to generate a series of squared numbers. Next, we'll see how to add a cumulative sum column to a dataset, specifically the air travel data. We start by setting the first value of the cumulative column to be equal to the first air value. Then, using a for loop, we add each subsequent air value to the previous cumulative total. This process helps us understand cumulative totals over a series. Finally, I want to highlight the importance of for loops in R. They enable us to automate repetitive calculations efficiently, which is essential when working with large datasets or performing iterative analyses. Understanding these basic structures is fundamental to becoming proficient in data analysis with R. Let's dive into some practical applications of loops in data analysis. First, we'll look at how to add a cumulative claim amount in health claim data using a for loop. This helps us understand the total claims over time, which is crucial for identifying trends and making informed decisions. Next, we'll create a delta variable in air travel data. This delta represents the difference between the current month's air travel number and the previous month's number. Calculating this difference allows us to see month-to-month changes, highlighting patterns or anomalies in travel behavior. Throughout this lab, the focus is on how for loops can simplify repetitive tasks in data processing. By automating calculations like cumulative sums and differences, we make our analysis more efficient and accurate. These examples connect directly to our overall theme of harnessing programming techniques to enhance data insights, making our workflows more streamlined and insightful. Now, let's take a closer look at some fundamental concepts in data analysis with R first. We have the user function. This is a basic template for creating your own functions. In R, you start with the function name, then define the arguments inside parentheses. These can be any variables you need. Inside the curly braces, you write the statements that make up your function. And finally, you include a return statement to output the result. This structure is key to making your code modular and reusable. Next, we have the distance function, which is particularly useful when working with spatial data. Here, we define a function called mydistance, which takes 4 parameters: x1, y1, x2, y2. These represent the coordinates of 2 points in a 2D space. The function calculates the Euclidean distance between them by taking the square root of the sum of the squared differences in each coordinate. This is a straightforward way to measure how far apart 2 points are, and understanding this calculation is essential for many spatial analysis tasks. Connecting these points to our overall theme, mastering custom functions like user function and understanding calculations, such as distance measurement, are foundational skills in data analysis. They allow us to write efficient, clear, and tailored code that helps us solve real-world problems more effectively. Let's take a closer look at this slide. Here, we're focusing on creating user-defined functions in R, which are essential for making our code more modular and reusable. The first function shown is mySumSquare. It takes a vector as input and calculates the sum of the squares of its elements. Notice how we initialize a variable sum to 0, then loop through each element of the vector, adding the square of each element to our sum. Finally, the function returns this total. This approach is quite versatile because you can reuse this function anytime you need to compute the sum of squares without rewriting the logic. We also see an example call, mySumSquare, C 1, 2, 3, 4, 5, 6, 7. This demonstrates how to pass a vector as input and get the sum of squares as output. Moving on, the slide mentions creating a function to calculate the absolute percentage difference between two values, with the second value as a reference. This kind of function is useful in many data analysis scenarios where comparing relative differences matters. Overall, the key takeaway here is understanding how user-defined functions can simplify complex tasks, improve code readability, and allow us to perform specific calculations repeatedly with ease. This aligns with our broader goal of mastering data analysis tools in R to handle real-world data efficiently. Welcome to this section on basic descriptive statistics. Here, we'll explore how to summarize and understand data effectively. Descriptive statistics give us a clear picture of the data's main features, making complex information more manageable. We'll focus on key concepts like measures of central tendency, mean, median, and mode, that tell us about the typical or most common values in our data. Additionally, we'll look at measures of variability, such as range, variance, and standard deviation, which help us understand how spread out the data points are. These tools are fundamental because they form the foundation for more advanced analysis later on. Understanding these basics is essential for making informed decisions and interpreting data accurately, which aligns with our overall goal of mastering data analysis techniques. Let's start by looking at how we load our data. Here, we're reading a CSV file named Health Claim from a specific directory on our computer. This step is crucial because it brings our data into R so we can analyze it further. Next, we examine the names of the variables or fields within this dataset using the names function. This helps us understand what kind of information we're working with, such as patient details, claim amounts, or dates. To get a quick sense of the data itself, we use the head function, which displays the first few lines. This gives us an overview of the structure and content of the dataset, ensuring everything loaded correctly. Now, focusing on the month variable, we use the table function to see how frequently each month appears in our data. This is important because it helps us understand the distribution of claims over time and spot any seasonal patterns. Finally, when we talk about descriptive statistics, we're referring to summarizing the main features of our data. These statistics, like mean, median, or mode, provide insights into the overall trends and help us identify any anomalies or interesting patterns. All these steps are fundamental in data analysis because they allow us to explore and understand the data before diving into more complex modeling or predictions. Welcome to this part of the data analysis course. I'm Venkat Reddy. Now, let's look at some summary statistics for our health claim data. First, we're checking the highest and lowest claim amounts to get a sense of the range. This helps us understand the spread and identify any outliers. Then, we move on to exploring the age variable. By using the table function, we can see the frequency distribution of different age groups within our dataset. This is useful for understanding the demographic profile of our claimants. Overall, these descriptive statistics are fundamental because they give us a quick, clear overview of the data's key features, setting the stage for deeper analysis. Now, let's look at the data analysis for the health claim dataset. First, we'll create a distribution chart, specifically a bar chart, to visualize the age distribution using the HIST function on health claim $age. As we examine this chart, we want to consider the shape of the distribution, whether it's bell-shaped, indicating normality, or if it's skewed to the right or left. Understanding the distribution helps us interpret the data better. Next, we'll analyze the number of medical bills. We'll generate histograms for the num medical bills variable, both with default frequency counts and with the freq equals t parameter to confirm the distribution. This step allows us to see how medical bills are spread across the dataset and identify any skewness or outliers. Throughout this process, we're focusing on descriptive statistics, which are essential for summarizing and understanding the key characteristics of our data. Recognizing the distribution shapes and patterns helps inform subsequent analysis and decision-making, aligning with our overall goal of extracting meaningful insights from health claim data. Let's dive into the data analysis process. First, we'll import the credit risk data to get started. Once we have the data, our next step is to find out the average monthly income of our customers, which gives us a sense of their financial stability. Then, we'll draw a histogram to visualize the age distribution of our customers. This helps us understand the demographic we're working with. Next, we're going to determine how many customers have less than 3 loans. That's important for assessing credit exposure. After that, we'll look at the frequency of customers with different numbers of loans, which reveals borrowing patterns within our dataset. Finally, in our lab, we'll focus on descriptive statistics. This is crucial because it helps us summarize and understand the key features of our data, enabling better decision-making. Throughout this process, our goal is to connect these steps to the bigger picture of credit risk analysis, using data to inform smarter lending decisions and manage risk effectively. Welcome to this part of the data analysis course with Venkat Reddy. Today, we're focusing on creating graphs. Graphs are fundamental tools in data analysis because they help us visualize data in a clear and intuitive way. When creating graphs, it's important to choose the right type of chart for your data. Whether it's a bar chart, line graph, scatter plot, or pie chart, each serves a different purpose. Remember, the goal is to make your data understandable at a glance. So, pay attention to factors like labels, titles, and scales to ensure your graph communicates the right message. Also, keep it simple. Avoid clutter and unnecessary details that can distract from the key insights. Creating effective graphs is a crucial step in the overall data analysis process because it allows us to see patterns, trends, and outliers that might not be obvious from raw data alone. By mastering this skill, you'll be better equipped to present your findings confidently and make data-driven decisions more effectively. Let's start by looking at the horizontal bar chart. As you can see, we're using the bar plot function with our counts data, setting loss equals 2 to rotate the labels for better readability, and making the bars horizontal with horiz equals true. This is a great way to visualize categorical data when labels are long or when you want a different visual effect. Next, we move on to creating a histogram. We've imported our web data from a CSV file located at this specific path. Once we have our data loaded into PriceWeb data, we can create a histogram to understand the distribution of the listing prices. Notice that we specify breaks equals 5 to divide the data into 5 bins, and we set the color to red to make it visually appealing. Now let's focus on creating a bar chart for the brand data. First, we generate a counts table by using the table function on the brand column. This counts how many times each brand appears in our dataset. Then, we use bar plot to visualize these counts. We also rotate the labels with loss equals 2 so they are easier to read, especially if there are many brands. Finally, I want to emphasize that creating various types of graphs in R, whether bar charts or histograms, helps us explore and understand our data more effectively. These visualizations are essential tools in data analysis because they reveal patterns, distributions, and relationships that might not be obvious from raw data alone. Let's start with importing the market data CSV file into R, which is the first step in our data analysis process. Once we have the data loaded, we'll create a histogram to visualize the reach. This helps us understand the distribution of reach values in our dataset. To make it more insightful, we'll customize the histogram by setting it to 10 bins and choosing a blue color, making the chart clearer and more visually appealing. Next, we'll move on to creating a bar chart that shows the number of campaigns by vertical. It's important to display all labels on this chart so we can easily identify each vertical category. After that, we'll change this bar chart into a horizontal format, which often makes comparisons easier, especially when there are many categories. Following that, we'll create a pie chart to illustrate the proportion of campaigns across different verticals. Pie charts are great for visualizing parts of a whole, so this will give us a quick snapshot of how campaigns are distributed. Now, let's import some petrol consumption data. With this data, we'll draw scatter plots to examine relationships between variables. First, we'll plot prop drivers' licenses against consum mil gallons, which can reveal if there's any correlation between the number of driver licenses and petrol consumption. Then, we'll create another scatter plot between petrol tax cents per gallon and consume mil gallons. This will help us analyze how petrol taxes might influence consumption levels. Throughout this process, remember that creating these graphs in R is a practical way to visualize data and uncover insights. The lab activity on creating graphs will reinforce these skills, showing how different types of visualizations can answer different questions about our data. Now, moving on to some of the advanced visualization techniques we can explore in our data analysis course. First, we have 3D graphs, which allow us to visualize 3 variables simultaneously, giving us a more comprehensive view of complex data. Then, there are lattice graphs, which are particularly useful for creating multi-panel plots that help us compare different subsets of data side by side. Next up are ggplot2 graphs, a powerful and flexible plotting system in R that enables us to build sophisticated and aesthetically pleasing visualizations with ease. We also have mosaic plots, which are excellent for displaying the relationships between categorical variables in a visual way that is easy to interpret. Correlograms are another key tool. They help us visualize correlations between multiple variables at once, often using color to indicate the strength and direction of relationships. Lastly, we look at advanced graph options, which give us greater control over the customization and presentation of our visualizations, ensuring they effectively communicate our insights. All of these tools are vital for making our data stories clearer, more impactful, and more engaging. Welcome to the data analysis course. I'm Venkat Reddy, and today we'll focus on analytics using R. R is a powerful tool for data analysis because of its flexibility and extensive libraries. Throughout this course, we'll explore how to leverage R to extract meaningful insights from data, which is a core component of making informed decisions. By mastering R, you'll be able to handle large datasets, perform complex analyses, and visualize data effectively. This aligns with our overall goal of equipping you with practical skills to tackle real-world data challenges. So, let's dive into how R can become your go-to tool for analytics. Let's take a closer look at some data analysis techniques using R here. We're working with a dataset on petrol consumption. I've loaded the data from a CSV file and used the head function to get a quick view of what the data looks like. This helps us understand the structure and identify the key variables. Next, we use the summary function to get basic statistical insights for each variable, like mean, median, and range. This overview is essential for understanding the data distribution and spotting any anomalies early on. We then look at the correlation between different variables, such as petrol tax, average income, proportion of drivers with licenses, and petrol consumption in millions of gallons. Calculating these correlations helps us identify relationships, whether variables move together or independently. Finally, I plotted the proportion of the population with driver's licenses against petrol consumption, using a purple color to clearly visualize the relationship. This visual aid makes it easier to interpret how these variables are connected. All of these steps, loading data, summarizing, analyzing correlations, and plotting, are fundamental in data analysis. They allow us to uncover patterns and insights that inform better decision-making, fitting into the broader theme of understanding data to make smarter choices. All right, let's walk through this slide. Here, we're working with a linear regression model, which we've called petrol reg. It predicts petrol consumption in millions of gallons based on the proportion of drivers with licenses. When we run the summary of this model, it gives us detailed statistics about the fit, including coefficients, p-values, and overall significance. Next, we look at the coefficients specifically with the coef function, which tells us the estimated change in petrol consumption for a unit change in the proportion of licensed drivers. The residuals, accessed via recid, show us the differences between observed and predicted values, important for understanding how well our model fits the data. The fitted function gives us the predicted petrol consumption values based on our model, which we can compare to actual data. We also perform an analysis of variance with ANOVA, which helps us evaluate the overall significance of the model by partitioning the variability. Moving on to visualization, we set up a layout for 4 plots to examine various aspects of our regression model visually. These plots are crucial. They include residuals versus fitted, a normal QQ plot, scale location, and residuals versus leverage. They help us check assumptions like linearity, normality, and homoscedasticity. Finally, we introduce a second regression model, petrol reg 2, which predicts petrol consumption based on petrol tax per gallon. This demonstrates how different predictors can be used in simple linear regression to explore relationships in our data. Throughout this process, the key takeaway is understanding how each component, coefficients, residuals, ANOVA, contributes to evaluating the quality and significance of our regression models. This is fundamental in data analysis because it helps us draw reliable conclusions about the factors influencing petrol consumption. Now, let's take a look at the data analysis involving multiple linear regression. Here, we're examining how different factors influence petrol consumption. First, I built a model called petrol multi-reg using the consumption in mil-gallons as the response variable, with the proportion of POP drivers with licenses and petrol tax per gallon as predictors. When I ran the summary, it provided insights into the significance of these variables and how well the model fits the data. Next, I developed a second model, petrol multi-reg 2, which adds average income in dollars as an additional predictor. Including income helps us see if economic factors further explain petrol consumption beyond licensing and taxes. When I look at this expanded model and its summary, I can compare it to the first to assess whether adding income improves our understanding of the data. The key takeaway here is that multiple linear regression allows us to analyze the combined effect of several variables on petrol consumption, helping us identify which factors are most influential. This approach ties into our overall theme of understanding the drivers behind energy usage, and it highlights the importance of considering multiple factors simultaneously to get a clearer picture. Now, let's take a closer look at how we build our logistic regression model using this dataset. First, we examine the data with the head function to understand its structure. Then, we specify our model, where we predict the probability of a serious delinquency within 2 years based on several key variables. These include utilization rate, age, debt ratio, monthly income, number of loans, and dependents. Notice that we're using GLM with a binomial family, which is standard for logistic regression. After fitting the model, we review the summary to understand the significance of each predictor. Finally, we generate predicted probabilities for each observation using predict, GLM, with type equals, response. This gives us the estimated likelihood that each individual will experience serious delinquency. These predicted values are essential for assessing risk and making informed lending decisions. Overall, this process illustrates how logistic regression helps us understand and quantify the factors that influence loan default risk. Thank you so much for your attention throughout this data analysis course. I hope you found it insightful and valuable for your journey in data-driven decision-making. It's been a pleasure sharing these concepts with you. Remember, the key to mastering data analysis is curiosity and continuous learning. Feel free to reach out if you have any questions or need further guidance. Once again, thank you for being such an engaged audience. I wish you all the best in your data analysis endeavors.